Hello, everyone. Thanks for the introduction. I'm Jawad. I work as a data scientist at GOJEK. And unfortunately, today my friend and co-presenter Willem from our data science platform team is unable to join us here. So I'll be representing him on the platform team's behalf. For a quick show of hands, can I know how many of you guys here are familiar with GOJEK? That's a good number. Let me start with a brief introduction to GOJEK. Indonesian cities are one of the most gridlocked places in the world, and two-wheeler transportation is one of the most efficient means to go from point A to point B and reach your destination. So if you've been to Jakarta or visited any Indonesian cities, it would be a common sight to spot a bunch of drivers hanging around coffee shops, under the trees or under the bridges. You can walk up to them and tell them your destination that you want to go, negotiate the price with them, and hop on a two-wheeler taxi. They will take you to your destination. These guys are honest, hardworking, but the only way to reach these motorcycle taxis is through footwalk. And in Jakarta and most Indonesian cities, sidewalks or footpaths are essentially non-existent. So there were an abundant supply of these drivers, and there was a latent demand for their service that they were providing. And this is a beautiful case of a marketplace problem that you can solve. And in 2010, GOJEK did not start as a tech startup, but it started as a call center operation, where you could ring up GOJEK offices, speak to one of the service desk agents, and then ask them to decide a match for you. They would in turn call back the drivers, negotiate prices with them, and dispatch the drivers to your pickup location. As you can see, this is not the most efficient way to solve a marketplace problem. And in 2015, GOJEK launched its first mobile app with 3 services. First one was Ride. Ride is nothing but a two-wheeler taxi service. Send, which is a courier service. You could send any parcel and get it delivered through the two-wheeler taxi drivers. Number 3 is Shop, where you can request the drivers to purchase something for you. So since then, GOJEK has transformed itself into a workday solution provider. By workday solution provider, I mean that you could take a GOJEK to go to your office, request your food or your lunch to be delivered through GOJEK. You can even top up your mobile payment balances using GOJEK's payment services. So moving fast forward today, this slide represents the scale at which GOJEK operates today. GOJEK has expanded to 4 countries, and it operates in more than 70 cities today. The GOJEK platform now handles more than 100 million transactions per month. And we are proud to say that the platform hosts and supports about 1 million plus drivers and about 250,000 merchants. Yes, GOJEK is one of the largest food delivery services in Southeast Asia outside of China. And there are about 17 product offerings that GOJEK supports today. And you can even order a professional masseuse to your place and get yourself relaxed. So when we expanded to different countries in Southeast Asia, we partnered with local tech talents, and we are called as Get in Thailand, and we are called as Go Viet in Vietnam. So this is a visualization which is plotted by taking the pings that are sampled from our drivers' mobile handset devices. This not only beautifully demonstrates the inflow and outflow of traffic in and out of the central business district of Jakarta, but it also gives you a scope of the magnitude of the task that the data science team in GOJEK is solving. My team is called as Mobility Data Science Team, and among other problems, we focus on matchmaking as well as pricing. So matchmaking is nothing but choosing the best driver for a given job, and pricing, in specific, surge pricing, estimates the price computed for a ride based on the ever-changing supply-demand scenarios from the real world. So this tweet really demonstrates the real challenge in industry today. It's one thing to build a model using Python, R, and scikit-learn, but it's a completely different set of challenges when you want to take the model into production and you want to scale the model. The model has to scale to millions of transactions, and it has to operate and make inferences in sub-second latencies. At GOJEK, every data science team is supported with a data science platform team who help the data scientists in taking a model from its infancy and deploy it in production and maintain the models in production. So for the rest of this talk, I'm going to focus on these things. I'm going to start discussing about the matchmaking problem. I'll walk through and frame what the problem is about, and some of the challenges that we faced in building the first ML pipeline at GOJEK. Later talk about the technical debt that we incurred over a period of time, and how we solved our technical debt with MLflow as one of our key components in our solution. So choosing the best driver for the job. If you guys have used Uber or Lyft or any ride-hailing services, you would have probably triggered a dispatch algorithm, something like this, right? When you're requesting for a booking, the naive dispatch algorithm would look for the list of available drivers around you and choose the best driver for you. Choosing the best driver itself, it could be a naive solution where you could take the driver who has the shortest straight line distance to the pickup location. But in reality, cars don't fly. So ground conditions and other traffic situations play an important factor in determining the ETA for the ride to arrive at your pickup location, right? And moreover, business has different meaning of the best match of a driver. In few cities, businesses want to optimize for the best customer pickup experience. In a few places, business want to optimize for good driver experience. And in some places, business want to optimize for, say, equality of opportunity given to all the drivers. Taking all these considerations into mind, we formulated a multi-objective optimization problem, and we started working on the DS solution for it. At GOJEK, this decision happens millions of times a day, and it's very core to how we make our matchmaking. It's core to our business operation, and it's core to improving our network efficiency in the marketplace system. So this was a first attempt at solving the problem. We have considered that we have hypothetically built a model to solve the multi-objective problem, but then as an organization, you're first developing a full-fledged ML pipeline to take the model into production environment, right? And I know that most of you would have faced this situation in the past or currently facing this problem. So as an organization, we had built an app which was scaling and performing well, but we had to start and build ML pipelines now. Of course, you could do this deployments manually every day and tune the parameters, but we want to make the entire pipeline automated. So we started to think about these things and started breaking down all the components that we want to build. First, we take a look at our raw data, and we know that we want to, at the end, have a model deployed in production, right? So the first step is we start with data processing. And with data processing, we process data from our data lakes, and we use Airflow as a tool to do it. At that time, Airflow was the most commonly used tool, and most of the data scientists were familiar in operating the Airflow. So you specify the sequence of steps that are executed as a DAG or a graph. And what Airflow lets you do is to break down your entire ETL pipeline into sequence of steps. And each step in the specific pipeline could be either a Python operator, you could swap it with a Spark job, or any other Beam job, or whatever it is. And Airflow has some really nice properties in the sense that it lets you handle the dependency between one step and the other step. So what happens when an existing step fails? How do you handle those failures? It also lets you define the number of times the steps needs to be executed again and again, so you can handle failures much better. So we stuck with Airflow, and we built all our ETL jobs and data processing jobs using Airflow. Thinking about deployment. The entire organization was using GitLab CI/CD system for its deployment, and we thought, why not adapt the same solution for ourselves? So for GitLab CI/CD, you define a YAML file in which you specify a series of steps. This ideal step for us would look like you build the staging serving application. You run a series of tests. It could be a functional test, load test, and make sure it is performing as intended in the staging environment. Then you build and package it in production environment. And we use Helm and Kubernetes to deploy our models in production server. Kubernetes, because it scales well, it's fault tolerant, and it's great for production environment. One important discussion about the GitLab CI/CD system is that it's a push-based system. So when your ETL training pipeline completes, what you do is you package all your artifacts, you train your model, and once your model is trained, you package your artifacts, your Docker containers, image, and then once everything is ready, you make an API call to GitLab, which then triggers the entire deployment pipeline. And this is very important in the way how we are going to make changes later. So what's in between these two steps? It's model training, which is the missing part. At that time, we were left with two options where we could build our own custom solution, which takes care of model training. And when you're in a rush to deploy models to production and to see the results of how your models are performing, you don't want to typically spend too much time on building custom solutions. So what we did was, as a natural extension, we started using Airflow to trigger the model training pipelines. And as a result of this, we got this specific architecture where Airflow, being an event-driven system, could be either triggered by a new partition which is created in your BigQuery table, or it could be triggered by specific times. And it starts to process the data, triggers the ETL pipelines, and then once it's a long-running ETL job, it triggers the model training. So when model trains, it produces a bunch of artifacts, like the evaluation test set, the model itself as a binary file, and a bunch of other Docker containers. Once all these artifacts are pushed, it's pushed to a repository, and then it makes sure that it calls the GitLab AI pipeline with the proper tag and with proper handling. Once that API call is triggered, GitLab takes over. It builds the system, tests, and deploys the application in production serving. So as you can see, at first, our models produced great results, so we were happy. And we were able to scale to millions of transactions, and this was working fine. At some point, the cracks began to show up. What was happening was, we understood that we built an entire monolith, which is triggered once, and it runs forever. When it completes, it's deployed the model to production. So some of the challenges that we faced in this particular approach, it was clearly evident to us that it is inefficient. We need to wait for long hours once the pipeline gets triggered. And say, suppose you are a data scientist, and you want to make some slight changes in either the model training procedure or the way the model serving is deployed. You cannot do these things without triggering the ETL pipeline, because it's one single step, and you have to wait until all the process gets completed. This was proving to be a really inefficient workflow for us. And then it's hard to experiment. Like I mentioned, one difference between a typical software engineering solution and a ML solution is that you keep experimenting when your model is live. So business comes with a request saying, hey, we think that these are some of the really important features for this specific business objective. Can you add to these models and test how they perform? In reality, when you have experience with ML solutions, most of your offline metrics, such as your AUC scores or your precision recall scores, do not exactly correlate with what you are producing offline. Maybe they don't correlate with your conversion rates or click-through rates and so on and so forth. So when you're making these changes, what you do is that you either create another branch in the repo and you make changes to your ML training pipeline so that your downstream or the GitLab pipeline understands these changes and then deploys it in the right fashion. Or you do fan in, fan out, where you have code flags in your model training system. You have dynamic flags to enable or disable a specific feature in the model, and then again you make changes, right? There's also another potential problem, which is the feedback loops of the model. And this we realized quite later, and this was one of the key concerns that we had. So when you're training a model and deploying it every day, and you're using the same model to make inferences, what happens is that you are now literally training on a different kind of data set whose distribution is affected by the model inferences that you make. This could sometimes be good, and sometimes it could cause a bad feedback loop. So what happens is that you really need to track all the model metrics, and in some cases, it's the feature importances that change over time, that drift over time as the feedback loop happens. And with this current architecture, we didn't have any way to test how our model is performing and what were the feedback loops that were going on in the system. The third thing is versioning. Since all your events are now triggered by Airflow and it's tightly coupled with Airflow, the entire pipeline is being versioned by the triggering time or the timestamp that is being called. So even your model serving or the deployment is a function of just this timestamp. Now what happens when you fork a new branch, train a new model? This gets really cumbersome. It's fine if your ETL jobs are being tracked by the timestamp, but it's not natural to track your model training pipelines, your models and artifacts with this specific timestamp. And this is one of the concerns that our data science platform team brought in. So as data scientists, when you're training a model, you have a fixed set of pipeline that prepares your features, but then you also have all your side inputs that go into the models. As data scientists, we hook up the model training with certain static files that we read from Google Cloud Storage or somewhere else. And what happens is that you lose the reproducibility when you're doing so. The code, which is version controlled and tracked, still remains the same. But because all your side inputs and dependencies have changed over time, you are not able to reproduce the same model that you have done before, right? And there was no standardized way to track these artifacts. Visibility. If you take a look at the CI/CD system, of course, it gives you some information about who made the change, which version of the branch you are running, and it gives also references to your git commit SHA. But the GitLab CI/CD system was designed for software engineering solutions. You don't see any information about features, models, or all the parameters that went into the model. Of course, you can log all these things in your pipeline, and you have to scroll through the logs and see what's going on. The second thing is, since the CI/CD system is push-based, your model training pipelines have now, let's assume that you are expanding from Singapore to Indonesia, Thailand, Vietnam. Now, all your model training pipeline has to know where to push these artifacts into production environments, and it has to remember everything that it has to do. And this becomes really messy in real quick. GOJEK operates on a scale of 17 different product services, and to have these pipelines remember all these artifacts and all these features, you really turn up building a messy system. This is also one of the concerns that were highlighted by the data science platform team. Role separation. When you're working on a complex ML pipeline, there are several different people working on it, and even several different teams working on it. So data engineers, whose job is to work on ETL pipelines, build features for the model, and data scientists who typically work on training different models, tuning the models, training with hyperparameters, and ML engineers who take the models and deploy them into production environment. Right now, once your entire pipeline is a single monolith, the ML engineer who is making some changes in your serving application is going to wait and trigger the entire pipeline and make changes throughout the code base, which is really messy and unnatural. So we went back to the drawing board, we analyzed all these issues, and we came up with a list of desired states that we wanted. And I list down some of the desired operations. First, we want to re-engineer the ML pipeline to make it easy to experiment. Means the data scientist should be able to make any changes in model training or swap out different model components and still able to see the result. We want to make results reproducible. So any side input or any features that goes into the model has to be tracked, version controlled, and it should be reproducible by anyone. And the problem of role separation, what we talk about here is that the data scientist deploying the model should be an afterthought. It should be quite easy to do, and he shouldn't play with all the configurations. Next, to track and evaluate the performance of model over time, not just one day or how one release performs, but how the model performs over a long period of time. And scaling to thousands of models should not be a complicated problem, and you shouldn't hard code or make a lot of change in your code base. So keeping all this in mind, we want to go and take a look at some of the options available. But in choosing certain tools, the tools change your design approach and design patterns that you configure in your systems, right? So we want to be mindful that we want a flexible tool where we don't want to change too much in our life cycle, but the tool should be able to adapt to our needs. And MLflow is one of such tools. So essentially, this on screen it's demonstrating a simple ML pipeline that you can see, where you start with data processing. You have your data lakes, and you start consuming data from your data lakes. You do data pre-processing. You run your ETL jobs. Then comes the model training part. Once the models are trained, you deploy the models in serving, and you see how the models are performing on the online metrics. And then the feedback cycle continues. Another important change in an ML lifecycle is that at every stage, you have different components, and data scientists would like to choose different components at different stage. Even in GOJEK, where you have multiple data science team, you cannot expect you cannot expect all the data science teams to use similar set of tools, because they are essentially solving different set of problems, and one tool which is used by one team may not be suitable for another tool by another team. So the workflow solution that you adapt should be able to support a variety of tools and not tie the data scientist in choosing a specific tool. And then in various stages, you have these tuning parameters, right? There are so many variations that go into the model, and as a data scientist, you want to optimize the model for its peak performance. You want to tune its hyperparameters. You want to swap in and swap out different models and see which is giving you the best results. So the workflow tool that we are using should be able to support these things. And then scaling. In a startup companies like GOJEK, the scale that you're tackling the problem changes rapidly over time. So you could expand to a few countries in like 6 months, and when you're scaling so fast, your entire pipeline should be able to scale with you. Your data lake should be able to support the new system. You should be able to swap out your Python pipelines with Spark pipelines. You should be able to change your model training from whatever that fits you. You should also be able to change your serving applications. You could choose between building your own Java serving application or using TensorFlow serving or whatever it is. Next is the model exchange. Now, typically, as you see, multiple teams and multiple people work in the entire pipeline. And once a model is being built by a data scientist, it should be packaged and used by another data scientist or ML engineer to transfer the model, take it, and deploy it in containers and Kubernetes servers. Next thing, which is quite often neglected, is the governance of the system. When you're building a new ML pipeline, you don't really think about how you regulate and track different artifacts that the entire pipeline produces. So this takes a backseat a little bit. But for data science platform team, this is one of the key components that they're looking at. And MLflow as a solution exactly solves all of these problems, right? And with MLflow, there's really not much change when you want to take the code from your local machine and into production, and you really don't have to change all your underlying components. It's a simple wrapper that you can build around, and then out of the box, it works fine for you. You can use the same code base with minimal change and deploy it in production, and it works everywhere. Today, as we stand, we'll take a look at some of the core components in the MLflow. The first one is MLflow tracking. MLflow tracking helps you to record and query different experiment configs. You can call an experiment run as one model training cycle, and it tracks all your code, the data that you are using to train the model, and all the side configurations and hyperparameters that go into the model. All these things are being tracked, and you can query them later on. And for MLflow projects, it's nothing but a standardized specification how you can wrap your GitHub repos or your source code bases. So it could be reproducible, and it could be run anywhere in the downstream, or any data scientist could extract the code and run it in his local machine. The third component is MLflow models. MLflow models helps you to package your already pre-trained model into a standardized format. So all your downstream components, such as deployment servers, are able to read this model and serve them. For our case, MLflow tracking was the most needed component, and let's dive deep into the functionality of MLflow tracking and how we implemented them in our solution. Before we start about the tracking, some of the key components in MLflow tracking are these. The parameters are nothing but your key value inputs to your code. So let's say you're training a model, all your learning rate for the model, the number of layers their neural network uses, all these hyperparameters and parameters can be stored as key value pairs. And metrics are nothing but the numerical values that the model produces. It could be your FN score, the precision recall, or whatever metric that you want to monitor and track. Artifacts could be just arbitrary files. In our case, the most interesting artifact is the feature importance of a given model which is trained. Even the trained model itself could be stored as another artifact as a binary file. And source tracks which version of the code you're using the git commit SHA. If you look at the simple UI, you'll be able to track all the runs within a given experiment, and you can see who was the user who created it, the source file that was used to train the model, the version. Along with this, you could also track a number of parameters, how the model performed while it was training. And one key important thing to notice here is that the metrics could be updated later on. I'll tell you how this becomes important when we look at the slides later. So this was our existing legacy workflow. It was one long-running job which had processing data, training models, and it was deploying into production serving. And what we wanted to do with this is we wanted to break this down based on responsibilities and concerns. So we started to decouple based on the concerns, and we broke down first into data processing, model training, and deployment, which seemed quite natural. And with Airflow, even Airflow has some gotchas. So we built a slightly modified version of Airflow, keeping its core functionality as the same, but building a lightweight wrapper around this to match whatever need that we had at that point of time. And we were using, usually the data scientists were familiar with using tools like Jupyter notebooks for training the models, and we wanted to abstract it away from the training pipeline. So Jupyter Notebooks were a key source in model training. And one important change that we made here was to incorporate GoCD for deployment pipeline. The key difference between GitLab and GoCD here is that GitLab was a push-based system in the sense that all your models need to be aware of the location where you had to push the models and call an API. But here, if you are turning into a pull-based system, what GoCD does is you can configure it to look for a specific location. It looks for a bunch of artifacts like models, version of the model, and so on, and it keeps polling the specific location. Whenever a new model is refreshed, it triggers the deployment pipeline. So now that we have data processing and model training, we need something in between for us to pass the data from data pipelines to our training models. And what we built was a feature store. A feature store is nothing but a polyglot storage service. It could be used for both storing the features as well as training the models. What we identified in our pipeline was that data scientists were using a common set of features to train different models, and having a feature store helped us to share the ETL pipelines, to share the features, and from then on, the models can be trained. The data science platform team has now open sourced the feature store, and it's available for free. And this is where the MLflow component sits in. It sits in between model training and deployment. Whenever you're training your models, it's a bunch of different hyperparameters. All you have to do is now to wrap your code and then push all your parameters and models and artifacts to model store and forget about entire complexity of the code base and making calls to the deployment pipelines. Once it is in model store, GoCD pipeline is going to poll for the features and artifacts and then trigger the deployment pipeline. So once we constructed that, these are some of the advantages that we have from a new system. First is asynchronous experimentation. Now, instead of if you want to make a change in your deployment serving or training your models, you don't have to trigger the entire pipeline from the beginning. Your ETL pipelines are run, and all your features are stored in the feature store. What you have to do is you could change different parameters in your model training, run them, track all the metrics, and essentially this is all the code that you have to add to track the metrics. You start it with a MLflow start run, and then you track all your model parameters, the metrics you want to track, and then you could also store your model itself as an artifact. Once all these components are stored in MLflow, the GoCD pipeline takes over and does its job. Next is reproducibility and traceability. Now, essentially, we have introduced these two components which keep track of all the artifacts and changes that you make. So feature store essentially tracks all your data sources, the jobs, the parameters. Now, MLflow tracks all your model hyperparameter tuning, your variables, your version of different models, and it even tracks your model itself. And the prod serving takes care of all other components such as Docker images, configuration for model deployment, et cetera, and et cetera. So additionally, in the pipeline, we have introduced just 2 more checkpoints for tracking and traceability. This is one of the data science platform team's favorite feature, model governance. Essentially, when the flow starts from the feature stores, you take the features, train your model, log everything in your MLflow, and then move to deployment. What happens after this is quite interesting. Since your MLflow lets you to track metrics even later on, you could collect all your offline metrics and online metrics such as click-through rate, conversion rate, and track it back to MLflow. You could go a step beyond and track all those features in your feature store so that the data engineer who builds this feature store now knows, hey, which features worked and which features produce the best results. You get a complete cycle of accountability, and you get a complete cycle of tracking system here. Here's another advantage about role separation. Now, these are the same different teams or these are the different teams that are working on the entire pipeline, but now they have well-separated roles. data engineer essentially works with data processing pipelines and feature store. Data scientist can focus on his job, and ML engineer takes over when you have to take the models to deployment. Now, everyone is familiar in their natural habitat, and this is one of the key advantages that you want to achieve. By converting these models from, by changing from GitLab, which was a push-based system, to a pull-based system now, what we have unlocked is scalability. Now, your model training or the data scientist doesn't have to worry about where he needs to deploy the model. He doesn't have to worry about if the Vietnam infrastructure is totally different from Thailand infrastructure or if the clusters are totally different. He just has to push the location, push all the models, artifacts, and other artifacts in the repository. And you can create a simple configuration file here, which looks for these different places and starts rolling out deployment. So this is another big advantage is that is unlocked because of changing the GitLab CI system from a push-based system to a pull-based system. So I can talk about, I can give a simple demonstration of how MLflow works, and let's start with it. So essentially, this looks like your typical model training pipeline, right? And what it does is that you can read data from your data sources. You can split your data into train, test, and you can train one of your models of your choice. And all you have to do here is to add these few lines of statements where you could start a MLflow run and log all the parameters, metrics that you want to track. Once you do this, you run the code like you would typically run any other code. You could change your hyperparameters, let it run, and once it is run, it is already being tracked by MLflow Tracker. So this is the UI that MLflow Tracker has. And your new run is already being captured here. So you can take a look at the historical runs that have happened in the past, and you can zoom in and see how all the metrics and parameters are being stored here. You could also tag your runs, and essentially what can happen is then the GitLab CI pipeline could refer to this tab. So you could tag your specific runs with specific tags, and MLflow has an API which lets you to poll which versions has updated. You could poll the API, and GitLab CI/CD Go CD pipeline could poll for all the changes and push the model into production. All the artifacts could be stored here. You could even have your feature importance graph or whatever diagnostic tools you want to capture. These could be stored. And the backend for this storage could be S3, GCS, or any storage bucket of your choice. Even though this looks quite simple, it's really a handy tool because without MLflow tracking, you have to go through all your historical logs to see how your models performed and how you have to track them. And one more really important and cool feature that we use is comparison of models. You could historically look at how each and every model performed, and you could choose any metric that you are tracking and see. This is just a toy example, but you could essentially take a look at historically how your offline metrics such as AUC scores differ when you're training models in the past. And this is a really powerful tool for us. Yeah, that's all for the demonstration from me. Thank you very much, guys.